Hello my dear students, you know you are in physics class and we are talking about rotational motion. And in rotational motion, if we are talking about energy, okay, rotational kinetic energy, translating kinetic energy, okay. So in this lecture we will talk about rotational kinetic energy. So let us consider a body, okay, a body moving about the center of mass, rotating about the center of mass with omega angular velocity. Hello my dear students, very good morning to all of you. You are in physics class and we are talking about rotational motion. And if we talk about the rotational motion, we have to understand the concept of rotational kinetic energy. So how we can define rotational kinetic energy? Let us see. Let us consider a body is rotating about an axis which is passing through the center of mass with angular speed omega. So the kinetic energy for rotational motion, kinetic energy for rotational motion, KER is equal to half I omega square. Okay. Same as it is, you know very well, formula for the kinetic energy for translatory motion, it is half mv square. Okay. So the kinetic energy, let us consider this body and the center of mass, this body is moving with velocity vc. Okay. In this case, if we are talking about the kinetic energy for rotational motion, we have to take moment of inertia about the center of mass. So the kinetic energy for the rotational motion is equal to 1 by 2 I about center of mass into omega square. But if we talk about the kinetic energy for translatory motion, what we can do? It is KET. Kinetic energy for translatory motion is half m velocity, it is the mass of the body and velocity of center of mass. In this case, we have to take velocity of center of mass, because if you want to differentiate rotational motion and translatory motion, what is meaning of translatory motion? When center of mass will move. So it is the kinetic energy for translatory motion. And if we talk about the total kinetic energy, so it is the total kinetic energy is summation of kinetic energy for rotational motion and kinetic energy for translatory motion. So it is half I about c omega square, we can write Cm plus 1 by 2 m Vc square. It is the total kinetic energy. So if we are talking about the kinetic energy, we have to consider both rotational plus translatory kinetic energy. If we are using conservation of energy in case of rotational motion, we have to use kinetic energy for rotational motion. If we are talking about rolling, in which translatory motion and rotational motion both simultaneously happening, then we have to talk both energies, kinetic energy for rotational motion plus kinetic energy for translatory motion. How? Let us see an example. If you are talking about the rotational kinetic energy, it is 1 by 2 I omega square. How we can derive it? So how we can derive? Let us consider a body, okay, and we can consider some differential masses. Let us consider m1, which is distance r1 moving with velocity v1, m2 having distance r2 from axis of rotation v2. Same as it is mi having distance ri, velocity vi, Mn, we are considering here n number of particles. So, Mn, Rn having velocity Vn. So, what is the total kinetic energy of each particle? The kinetic energy is equal to half m1 v1 square plus half m2 v2 square up to half mn vn square. Okay, we can write this in form of summation I equal to 1 to n 1 by 2 mi vi square, and you know very well relation between angular, this body is rotating with angular speed omega, and relation between this vi and omega is omega into ri. We can put in this above expression, we will get 1 by 2 summation I equal to 1 to n mi ri square, okay, into omega square, and this expression what we can write, it is the moment of inertia, which is I equal to 1 to n summation I equal to 1 to n mi ri square about the center of mass. So, the kinetic energy is equal to 1 by 2 I about the center of mass omega square. Very easily we can derive it.